What is spacecraft attitude control and how does it work? Imagine trying to keep a spinning top perfectly balanced while it moves through space. That's similar to what spacecraft attitude control does. It's all about managing how a spacecraft is oriented in space. Whether it's pointing a camera at a planet or aligning antennas for communication, precise control is essential. In electrical engineering, this process is a closed-loop feedback control system. It starts with sensors that measure the spacecraft's current orientation. These sensors include gyroscopes that track angular velocity, star trackers that identify star positions, sun sensors, and magnetometers. Because each sensor has some noise or error, the system combines their data using techniques like Kalman filtering to get a reliable estimate of the spacecraft's attitude. Once the system knows the current orientation, it compares it to the desired attitude. The difference between these two is called the error signal. Control algorithms, often based on proportional integral derivative controllers, process this error. They calculate the exact amount of correction needed. These algorithms consider the spacecraft's rotational dynamics, which are nonlinear but can be simplified for slow movements. Next come the actuators, which are devices that make the physical adjustments. Reaction wheels are common. They spin at different speeds to produce torque without expelling any mass. Control moment gyroscopes use spinning rotors and gimbals to generate larger torques. Magnetic torquers interact with Earth's magnetic field to produce torque, and thrusters are tiny rocket engines that push the spacecraft in the right direction. Internal actuators change the spacecraft's angular momentum, while external ones work by interacting with the environment. The entire process is a continuous feedback loop. The system keeps measuring the attitude, calculating errors, and sending commands to the actuators. This loop runs automatically onboard, often at less than 1 cycle per second to avoid vibrations. It also has to handle disturbances like gravitational pulls, solar radiation pressure, or residual atmospheric drag. Attitude can be represented in different ways, such as Euler angles, direction cosine matrices, or quaternions. Quaternions are often preferred because they avoid issues like gimbal lock and are numerically stable. In simple terms, spacecraft attitude control is a system that uses sensor data to figure out where the spacecraft is pointing, then uses control algorithms to decide how to adjust its orientation, and finally commands actuators to make those adjustments. This process keeps the spacecraft pointing accurately for communication, imaging, or scientific tasks. Electrical engineering plays a key role in designing the sensors, control algorithms, and actuator systems that make all this possible.